Welcome back, everyone, for another deep dive. Today we're gonna be kind of going back in time, right? Like way back, trying to understand all the crazy ways the Earth's climate has changed over millions and millions of years.
Yeah, it's quite a journey.
It really is. And you all have sent us a ton of research on this, which is amazing. We've got stuff about ice ages, heat waves, you name it. And trying to make sense of it all, well, it can feel like, I don't know, assembling a puzzle in the dark, right?
It really can.
So that's what we're here to do, shed some light on this whole climate change puzzle. Because if it's true that the Earth's climate naturally goes through these crazy ups and downs, these big swings, how worried should we be about the warming we're seeing now?
That's the ultimate question.
Yeah.
And to answer it properly, we got to go way, way back in time. See, long before humans entered the picture, planet Earth was already putting on quite the temperature show. We're talking some really wild swings.
Oh, I believe it. Like, way more intense than anything humans have ever experienced, right?
Absolutely.
I've read about things like the Great Oxidation Event, which just sounds insane. When oxygen first flooded the atmosphere. Talk about a game changer.
Absolutely. It completely transformed life on Earth. It was a huge deal. But to really wrap our heads around the scale of these changes, we need to start thinking in terms of deep time. We're talking about geologic timescales here, periods so vast that human history looks like a tiny blip, almost invisible.
Right, like comparing a grain of sand to a mountain.
Exactly.
Yeah.
So let's take the Phanerozoic eon, for example. Now, that spans roughly the last 540 million years.
540 million. Wow. Okay, so what? Dinosaurs and...
Exactly. That's when most of the plant and animal life we're familiar with evolved. Dinosaurs, early mammals, the whole shebang.
Amazing. So, okay, paint us a picture. What was the climate like back then, during this Phanerozoic era?
Well, you might be surprised to learn this, but for the majority of the Phanerozoic, for most of those millions of years, Earth was actually much warmer than it is today.
Really? Like, how much warmer are we talking here?
I mean, significantly warmer. I'm talking palm trees in Antarctica kind of warm.
Wait, hold on. Palm trees in Antarctica? You're telling me it was warmer then than it is now, even with all the concerns about, global warming and climate change?
Yes, that's exactly what I'm saying. Research by Scoties in 2018, and this is really interesting, it indicates that our current climate right here, right now, is actually colder than 95% of the Phanerozoic eon.
Wow, 95%. Okay, so then what's going on now? Why is it so cold?
Well, geologically speaking, we're currently living in what's called an icehouse climate.
Icehouse climate.
Yeah, and that just means that we have permanent ice sheets at both poles.
Oh, I see. So it's not that it's literally an ice house, but because we have ice at the poles?
Precisely.
So that's pretty unusual for Earth, right? To be in this, ice house mode.
Yeah, in the grand scheme of things, it's actually relatively uncommon, at least based on what we know from the Phanerozoic.
Okay, so we're already busting some major climate myths here.
Right. But it gets weirder. We're talking about, let's say, 26 to 14 million years ago. This is during the late Oligocene to the mid-Miocene periods. Don't worry too much about the names.
I'll just nod along.
So during that time, the planet was running super hot, really warm, even though CO2 levels were way lower than they are today.
Now, wait a minute. Hold on. That doesn't seem fair at all. How can it be so warm back then with low CO2? Everyone always says that CO2 is the big driver of temperature.
You're right. It's a really important point, and it highlights why we need to look at more than just CO2 when we talk about climate. See, understanding how heat moves around the globe, it's something called meridional transport. It's really crucial here.
Meridional transport.
Yeah, and it basically means that it's not just about the total amount of energy we get from the sun, it's also about how that energy is distributed across the planet.
Oh, I see. So, even if the total amount of sunlight stays the same, the way it's spread out can make parts of the Earth warmer or cooler.
You got it. It's kind of like, imagine different parts of your house being warmer or cooler depending on where the vents are, even if the thermostat is set to the same temperature throughout the entire house.
Oh, that's a good way to put it. So something besides just CO2 was driving those ancient heat waves way back then, and this whole meridional transport thing is a big clue.
Exactly. It suggests that other factors, like ocean currents and variations in Earth orbit, have also played a major role in climate change throughout our planet's history.
So it's a much more complex picture than just CO2.
Right, and understanding those factors is absolutely critical for understanding our current situation as well.
Yeah.
But to really get a grip on how these forces interact, we need to zoom in on a more recent, but equally dramatic period, the Ice Ages.
Ah, yes, the Ice Ages. Those are some serious climate swings. We're talking massive ice sheets covering huge parts of the continents, then retreating, then advancing again. It's enough to make our current climate anxieties seem a bit, I don't know, insignificant.
Yeah, they really put things in perspective, don't they? And those glacial cycles, they weren't just random events either. They followed a pattern, and they were heavily influenced by what are known as the Milankovitch cycles.
Milankovitch cycles. Okay, that sounds kind of intimidating. What are those exactly?
Well, imagine Earth doing this really slow, graceful waltz around the sun.
Okay, I'm picturing it.
The Milankovitch cycles, they describe how the way our planet moves and tilts, how that changes over really, really long periods.
Oh, interesting.
And these subtle shifts in our planet's motion, they affect how sunlight is spread across the Earth, which in turn influences the growth and retreat of those massive ice sheets that characterize the ice ages.
So it's not just about how much solar energy we get overall, but also about where that energy is hitting the Earth.
Exactly. Imagine like a giant spotlight shining on, say, a beach ball. If you tilt the ball or move it closer or farther from the light, the brightest spot changes, right?
Yeah.
It's kind of like that for Earth and the sun. And these Milankovitch cycles, they're like the choreographer of that dance.
That's a great analogy. So these cycles have been like the conductors of the ice ages for millions of years.
That's right. And we can actually see the effects.
Oh, really?
Yeah. In ice cores, ocean sediments, they all record the fingerprints of these orbital shifts going back millions of years. It's pretty remarkable.
That's incredible, like hard evidence of these cycles playing out over eons. But here's a thought. Within those big, long ice age cycles, there were also these really sudden temperature swings, right? Those like really fast warm-ups called Dansgaard-Oshur events. Those seem way too fast for those Milankovitch cycles to explain.
You're absolutely right. Those rapid temperature jumps within the ice ages, they're still a bit of a head-scratcher for scientists.
It's like Earth gets impatient with the slow pace of the ice ages and decides to just like fast forward to the warm part.
Kind of. We call them Dansgaard-Oshur events, or DO events for short. They're like little blips in the system.
Little blips that could warm the planet incredibly fast, right? I mean, we're talking decades, not millennia, which is just mind-boggling when you think about it in geological terms.
It's true. And they weren't just localized events either. They left their mark pretty much all over the globe.
So wherever scientists look, whether it's ice cores from Greenland or sediment layers from ancient lakes, they see the same thing.
Exactly. A really clear pattern emerges.
Ooh.
A sharp, sudden increase in temperature, kind of like a spike, and then a slower, gradual decline back to what were considered normal ice age conditions.
Like a roller coaster that suddenly shoots uphill and then gently coasts back down.
A good way to put it. But figuring out what exactly triggered these abrupt climate hiccups, well, that's a tough nut to crack.
So what are the leading theories? What do scientists think might have caused these DO events?
The exact trigger is still being debated. But a lot of scientists believe it has something to do with changes in ocean currents, particularly in the Atlantic.
The Atlantic Ocean, how so?
Well, one idea is that large influxes of fresh water, probably from melting glaciers, could mess with the circulation of warmer water from the tropics up towards the poles.
Oh, interesting. So it's like disrupting a carefully balanced system.
Exactly. Imagine, like, clogging up a radiator system and suddenly the heat can't flow properly.
And weren't there also those Heinrich events happening around the same time? Those massive iceberg armadas? I remember reading about those and thinking it sounded like something out of a disaster movie.
Yeah. Talk about throwing a wrench in the system. Heinrich events are when you see these huge deposits of debris in ocean sediment layers that could only have gotten there if massive, and I mean truly massive, numbers of icebergs had broken off from ice sheets and carried those rocks and sediment with them as they drifted out to sea.
Wow, so it wasn't just a few ice cubes clinking around in the ocean. We're talking like entire glaciers breaking apart.
Pretty much. And the timing of these Heinrich events often overlaps with those rapid DO warning periods, so there's definitely a connection there, although the exact relationship is still a bit of a mystery.
It's like trying to solve a giant jigsaw puzzle where the pieces keep changing shape.
A very accurate analogy. But let's try to put all of this into perspective. So far, we've been talking about these long, slow Milankovitch cycles, setting the stage for the ice ages, and then these quick, sharp DO events and Heinrich events adding their own plot twists.
It really makes you appreciate just how dynamic and unpredictable Earth's climate can be.
Absolutely.
Yeah.
But for now, let's shift gears a bit and fast forward out of the ice ages to a time a little closer to home, the Holocene.
Ah, the Holocene, our current interglacial period, right? Starting around 11,700 years ago, if I remember correctly.
You got it. And compared to those crazy swings of the ice ages, the Holocene has been relatively stable, which is a big part of why human civilization has been able to thrive.
That makes sense. It's during this period that we went from hunter-gatherers to building cities, developing agriculture, writing books, all that good stuff.
It's true. The Holocene has been pretty good to us, relatively speaking at least.
Yeah, it almost sounds like we've had it a little too easy, especially when you compare it to, like, massive ice sheets and wild temperature swings.
It's all about perspective, right? But even within the Holocene, even within this period of relative stability, there have been some notable climate fluctuations, and understating those is crucial if we want to accurately compare them to the warming we're seeing today.
You're talking about periods like the Holocene climatic optimum, right? When temperatures were actually warmer than they are now, even without any help from humans.
Precisely. It's another great example of how things aren't always as straightforward as they might seem.
Okay, tell me more. I love when things get complicated.
So the Holocene climatic optimum, or the HCO, was a period roughly 9,000 to 5,000 years ago when global temperatures were, on average, a bit warmer than they are right now. And this poses a bit of a puzzle for some climate models, which struggle to replicate this warm period without factoring in natural variations beyond just CO2.
So it's like Earth decided to have a natural heat wave, even though, according to some theories, it shouldn't have been so warm back then.
It's true. And this is a really important point because the HCO really challenges that assumption that any warming beyond pre-industrial levels is automatically unusual or entirely caused by humans. It tells us that there are still things about the climate system, about how it naturally fluctuates, that we don't fully grasp.
So even within this relatively stable Holocene period, there have been these significant temperature swings. It really makes you wonder what other surprises Earth's climate history might hold, right?
Exactly. And speaking of surprises, let's narrow our focus even further. We've talked about cycles spanning tens of thousands of years, but there's also this fascinating 2,500-year cycle called the Bray cycle, which has been linked to some major events in human history. And that might be connected to something even bigger than what we've discussed so far.
Okay, now you've got me hooked. Tell me more about this Bray cycle. What is it, and what kind of historical events are we talking about here?
Okay, so we've covered a lot of ground here. It's clear that Earth's climate has a history of being, well, a bit dramatic. Ice ages, heat waves, those sudden swings. It's enough to make you wonder if we should be investing in both parkas and swimsuits just to be safe. All right, it's a wild ride, but the million-dollar question remains. How much of the warming we're experiencing right now is part of this natural drama, and how much is our doing? That's what we really need to figure out.
Exactly. We've been looking back through the history books, so to speak. So where does modern global warming, this MGW everyone's talking about, where does it fit in? Is it just another one of Earth's natural warm spells? Or have we humans actually messed with the thermostat?
Well, that's the crux of the issue, isn't it? It's like trying to figure out if a cough is just a little tickle in your throat or a sign of something way more serious.
Yeah.
We need to diagnose what's happening now within the context of Earth's long-term health record, which is what we've been trying to do here.
And that record, from what I'm gathering, suggests that Earth's climate has a serious case of the wandering temperatures. So where does that leave us with modern global warming? Are we just in another natural warm spell, or have we, cranked the heat up too high?
Well, here's the thing. It's probably not an either-or situation. Earth's climate is a really complex system, way more complex than we can probably even imagine, and it's influenced by all these factors working together. Some of them are natural, and some of them are definitely human caused.
Okay, so it's not as simple as just pointing the finger at human activity and saying, you broke the climate.
Not quite. Yeah. It's definitely more nuanced than that. I mean, there's absolutely no doubt that human activities, especially burning fossil fuels, are pumping more greenhouse gases like CO2 into the atmosphere. But the big question, the one scientists are wrestling with, is how much of the warning we're seeing right now is directly because of those human activities? And how much of it would have happened anyway just because of those natural variations we've been talking about?
So how do you even begin to untangle that? How can scientists possibly determine what's natural warming and what's human-caused when they're both happening at the same time?
That's the real challenge. It's really, really tough. A lot of it comes down to modeling. Scientists create these complex computer simulations, almost like digital twins of Earth, and then they run all sorts of experiments on them. Yeah, they'll plug in everything they know, all the data they have, past climate variations, volcanic eruptions, solar activity, human emissions, and the whole 9 yards. And then they see how well the model's predictions line up with the actual temperatures we're seeing in the real world.
So it's like a giant experiment, but instead of test tubes and beakers, they're using computer code and climate data.
Exactly. And these models have become so sophisticated and detailed, it's incredible. But even with all that, they're still just representations, representations of this incredibly complex and chaotic system. So there's always going to be some degree of uncertainty.
Right, like trying to predict the exact path of a leaf in a hurricane. It's just...
Right. And that's the tricky part, because it makes it hard to say for sure what percentage of the warming we're seeing is natural and what percentage is us.
Okay, so even with all this amazing research and those high-powered computer models, it's still tough to definitively say, okay, humans are responsible for X% of the warming, case closed.
Exactly. It's a constant process,
Yeah.
Always more research, always refining the models. There are always going to be different viewpoints, different interpretations of the data, and that's science. But if there's one thing that's becoming super clear, it's that we can't just focus on one single scenario, one fixed outcome. We need to be ready for a range of possibilities for whatever the climate throws at us.
That makes sense, especially since Earth seems to have a bit of a flair for the dramatic when it comes to climate change, if you know what I mean. But if we zoom out a little bit, if we look at the big picture of Earth's history, what does it tell us about what the future might hold? Like, what's the long-term forecast?
That's the big question, right? And if there's one key takeaway from everything we've talked about today, from our deep dive into the past, it's that Earth's climate is never really static. It's always changing, always in flux. And we know, for instance, that right now we're in what's called an interglacial period, which just means it's a period between ice ages.
Right, like a brief intermission between those big dramatic acts.
Exactly. And like we discussed earlier, those interglacial cycles, those big swings, they're driven by those slow and steady Milankovitch cycles, those changes in Earth's orbit that affect how sunlight is distributed.
And those cycles, those aren't going to just start happening just because we're worried about global warming, right?
Exactly. Those are fundamental to how our planet operates, how it interacts with the sun. They've been happening for millions of years, and they're going to continue long after we're gone. So what does that mean? It means that even if we somehow manage to completely reverse all human-caused warming, even if we went back to, like, pre-industrial levels of CO2, a future ice age is probably inevitable.
Okay, so that's kind of a big deal, isn't it? We spend so much time and energy worrying about the planet getting too warm that we sometimes forget that it also has a history of getting really, really cold.
It's true, we often focus on one side of the coin, but the reality is we need to be prepared for both possibilities, a warmer future and a potentially much colder one. It's about being resilient, adaptable, and ready for whatever curveballs Earth decides to throw our way.
So how do we do that? How do we even begin to wrap our heads around preparing for something as massive as an ice age? Where do we even start?
It might seem daunting, but there's actually a lot we can learn from the past. Think about it. During the last glacial period, humans not only survived, but they thrived in some pretty harsh conditions. They adapted, they innovated, they figured it out, and we have their ingenuity to learn from.
That's right. They didn't have the luxury of debating the science or arguing about the causes. They just had to adapt. Or, well, not adapt.
Right, and they developed ingenious hunting strategies, they created warmer clothing and more effective shelters, they figured out ways to store food for those long, harsh winters. We can look to their resilience, their ingenuity, for inspiration.
Like they say, history might not literally repeat itself, but it often rhymes.
I like that. And it's true, those echoes of the past, those adaptations, they could provide us with some pretty valuable lessons for how we face our own climate challenges. But we're not starting from scratch, right? We have so much more technology at our disposal now than our ancestors could have ever dreamed of. We've got science on our side.
Exactly. So how can we use those tools, those advancements, to not just survive, but to thrive in a potentially colder world?
Well, we can start by thinking about developing even more energy-efficient technologies. We can explore different agricultural practices, ones that are better suited to those colder climates. And there's always geoengineering, although that comes with its own set of questions and considerations. The key is that we don't just react to the changes as they happen, but that we try to anticipate them, to plan ahead and have solutions ready.
It's about being proactive, thinking ahead, rather than just reacting after the fact, which is exactly what this deep dive has been all about.
I completely agree. We've spent a lot of time looking back, digging into the incredibly deep and fascinating history of Earth's climate. But what really matters now is how we use that knowledge, that understanding, to shape a better, more sustainable future for ourselves.
Well said. So as we wrap up this deep dive into Earth's incredible climate journey, what's the most important takeaway for our listeners today? What do you hope they'll remember most?
If there's one thing you take away from all of this, it's this. Climate change isn't something new.
It's not just a modern problem. It's an integral part of Earth's story, a story of constant change, adaptation, and resilience. And by understanding that long view, those epic cycles, the ice ages, those warm periods, the influence of the sun and Earth's movements, the incredible tenacity of life on this planet, by grasping all of that, we can face the challenges ahead with hopefully a little more knowledge, a bit more wisdom, and a lot less fear. Because knowledge really is power, especially when it comes to something as important as climate change.
Beautifully said. It's not about panicking. It's about being informed, prepared, and adaptable. And the more we learn about this amazing planet we call home, about its long and complex history, the better equipped we'll be to navigate the challenges ahead, no matter what those challenges might be. Thanks for joining us for this incredible journey through time. And until next time, keep exploring, keep asking those tough questions, and keep learning.